Ah, yes, the beautiful wireless LAN, ccna, what is this, ccna3, number 4. Okay, so this one is great because Cisco says you don't have to do this chapter. The only catch is, in the final, they have questions over this chapter. And as far as I can see, they're graded. Anyways, we want to know about wireless a little bit anyway, so we're just going to go over it anyhow. So in this chapter, we're going to describe wireless LAN technology and standards, describe the components of a wireless LAN infrastructure, describe wireless topologies, describe the 802.11 frame structure, describe the media access method used by wireless technology. I know you guys already know that is collision avoidance. Describe channel management in a wireless LAN. Describe threats to wireless LANs. Describe wireless LAN security mechanisms. Configure a wireless router to support a remote site. Configure wireless clients to connect to a wireless router. Troubleshoot common wireless configuration issues. Sounds like a good time. Here we go. Supported mobility. What's the primary use for wireless LAN? So we can bring our beloved tablets, laptops, and whatever else, use phones, use wireless. And then that's why BYOD became popular, because everybody was doing this, but then they need to have the right permissions and make the network secure, and so we get the BYOD, right? Or mobility. These are what people are using. Here's access points. I'm sure you've never thought about how wireless floats around a house. Well, if you haven't, here we go today. We have TVs using it, laptops using it. Apparently this phone is using it, unless that's part of the computer. I don't know. Maybe that's wireless NIC. This phone is. Alright, so lots of stuff connect to this poor little wireless integrated services router. And so that's why we have to learn about it. Alright, so just as with LANs, we have our own different types of wireless networks, I guess, right? So we have Bluetooth, right, which we talked about this before, that it's a PAN, but actually it's a wireless PAN, right? WPAN operates in the range of a few feet. Wireless LAN operates in the range of a few hundred feet, such as in a room, home, office, or even a campus environment. So maybe a few buildings if we have extended SSIDs, or extended service sets, sorry. ESS. Wireless wide area networks, WWANs, range of miles, such as a metropolitan cellular hierarchy, or even intercity links through microwave relays. So they're going to say there are 3 different technologies right there. So on this wireless WAN, we're going to be doing cellular. It could be WiMAX. Actually, it could be Wi-Fi, or I would guess it would even be satellite, even though they didn't say that there, where they don't have satellite here. Alright, so we'll go over them. Bluetooth provides PAN. You guys probably use it every day. Wi-Fi, wireless fidelity, and IEEE 802.11 wireless LAN standard, commonly deployed to provide network access to home and corporate users to include data, voice, and video traffic to distances up to 300 meters. WiMAX, worldwide interoperability for microwave access, and IEEE 802.16 WWAN standard that provides wireless broadband access of up to 30 miles or 50 kilometers. WiMAX is an alternative to cable and DSL broadband connections. Mobility was added to WiMAX in 2005 and can now be used by service providers to provide cellular broadband. Cellular broadband consists of various corporate, national, and international organizations using service provider cellular access to provide mobile broadband network connectivity, first available with second-generation cell phones, 2G, with higher speeds becoming available in 2001 and 2006, part of the third generation and fourth generation, 3G and 4G, of mobile communication technologies. Satellite broadband provides network access to remote sites through the use of a directional satellite dish that is aligned with a specific geostationary Earth orbit satellite. It is usually more expensive and requires a clear line of sight. Okay, here we keep going. Radio frequencies. Well, wireless communication is supported by very low frequency, and you guys can look through, and I think it tells you what these different ones do. If that interests you, go there, but basically it's just saying, hey, how is this wave formed? Is it this big? Or is it this big? Or something like that. Okay, so let's look at what we actually care about here. Alright, so the 2.4, probably the best right now. 5 gigahertz, not as good. Why? It's not going to go as far because the wave is bigger and it's easier to get distorted. It's great if we have line of sight. And the 60 gigahertz, I have to guess, is really good if we have line of sight. Otherwise, it's worthless, but probably going to be used by ISPs to fire from one point to another and get a whole lot of data. So let's move on. Alright, so here, you can read down here, and it's going to tell you a whole lot. I'm just going to summarize these. Actually, I might read the AD, because it's newer. Alright, so 802.11, first test of wireless, 2.4, 2 meg, slow, okay. Then they brought out A, and A was very short-lived, right? It was sweet because we got a whole lot more speed than we had before. We went from 2 meg to 54 meg, but it had this 5 gigahertz, and as I just said, this one does not go very far, and especially in this technology, you could only be about, you know, probably 20-30 feet away from it. If it was going through a wall, then it didn't work. So what killed it? We went to 802.11b, which once again was on the 2.4 gigahertz, but instead of having 2 meg, had 11 meg, and we could actually be fairly far away from this, and it was great. Then we went to G, and G brought us back up to those A speeds, but still ran on the 2.4. It was backwards compatible with anything that ran on the 2.4, which before that was 802.11b. Okay, so then we go to N. And you see the 600 meg, it's kind of a lie. This did not happen to the third wave, which was, I don't know, probably 2 years ago. And you had to have a special NIC. You need basically almost like a double NIC to get this kind of speeds. Otherwise, you're just going to get 300. Would be your max, and you have to be using encryption and all this. Like, you can't, if you have it open, you max out at, I believe, a little higher than this 54 megabytes, but you're basically getting G speeds if you are using open authentication. So you need an advanced authentication to actually get the speeds and a fancy NIC. Alright, so what was cool about it though, it ran on 2.4 and 5, which means it was compatible with A, B, and G on the backwards style. But to get our fastest speeds, we're going to have the 5 gigahertz and fancy stuff going on. Then we went to AC. Okay, so AC is only 5 gigahertz. Why do I think it's going to die soon? It's only 5 gigahertz. Because they come out with this 2.4, so if you're buying access points, you have to double or triple how many access points you put in a building if it's 5 gigahertz, rather than going to the 2.4. So AD will probably kill it, right? And AD has even faster speeds. I have not tried AD. I don't believe it's ratified. But AC is, we do have it in the classroom, and it does not, I'm not getting quite this much speed, but I think I was getting on 800 meg on it, so it is pretty fast. Okay. Well, let's see what it says about AD now. Scheduled for release in 2014 and also known as WiGig, it uses a tri-band Wi-Fi solution using 2.45 gigahertz and 60 gigahertz and offers theoretical speeds of up to 7 gig. Notice that's 7 gig. They have waves of this technology where it gets faster and faster. However, the 60 gigs band is a line of sight technology and therefore cannot penetrate through walls. When a user is roaming, the device switches to lower 2.4 and 5 gigahertz bands. It is backwards compatible with existing Wi-Fi devices. However, supporting a mixed environment limits the expected data rates. Okay. Wi-Fi certification. Well, who came up with this Wi-Fi thing, this wireless fidelity, and what does it ever mean? Free Wi-Fi? What does it mean? Alright, so if it's Wi-Fi certified, it's a generic Wi-Fi Alliance logo stating that the product has been tested and meets the specified Wi-Fi feature. What does that mean? It means that you can use Wi-Fi devices with Wi-Fi devices. So that's all that really means. So saying free Wi-Fi, I guess you're saying that you're allowing Wi-Fi devices over your wireless, but most people think it means wireless internet. But really, it's just saying it's supported. The other ones kind of make, let's see, direct Wi-Fi certified. Let's see what this one means. Certifying that a device is Wi-Fi direct capable. Simplifying the sharing of media between devices. Okay, super cool. What else do we have? Those are IEEE, I believe. Oh no, that's just Wi-Fi Alliance. It's a non-profit industry trade association devoting to promoting the growth and acceptance of wireless LANs. It is an association of vendors whose objective is to improve the interoperability of products that are based on the 802.11 standard. Okay, so who came up with the 802.11 standard? The IEEE. It specifies how RF is modulated to carry information and maintains the standards for local and metropolitan area networks. With the IEEE 802 LAN MAN family of standards, the dominant standards in the IEEE 802.11 family are 802.3 Ethernet and 802.11 wireless LAN. Although the IEEE has specified standards for RF modulation, it has not specified manufacturing standards. Therefore, interpretations of 802.11 standards by different vendors can cause interoperability problems between their devices. But the Wi-Fi Alliance says, hey, no, we're going to be on these standards and it's going to work. Okay. And then what is the ITUR? Regulates the allocation of RF spectrum in satellite orbits. So it tells us what bands, the 2.4 gigahertz and 5 gigahertz, we can use without going to jail, I guess, right? Who else helps regulate that? The FCC. Comparing wireless LANs to a LAN. Well, shocker here, guys. You don't use wires. Alright, so that's the first thing. What does it use? RF radio frequency versus a cable connection. The media access, CSMA. For Ethernet, we know it's collision detection. That back off algorithm that says, hey, after a collision, we're going to send a random timer out to get everybody working again and hopefully don't have another collision. What is wireless use? Collision avoidance, CA. Availability. Anyone within range of the radio NIC to an access point can get on. Otherwise, on Ethernet, you need a cable connection. Signal interference. Yep, in wireless there definitely is. Lots of stuff interferes with it. Ethernet, apparently it's inconsequential. Alright, so that took me long enough to get out of there. You can thank Grangeville Schools for that. Alright, so now signal interference is not important for Ethernet. I think so. That's why we like fiber better, right? Because it doesn't really get interfered with, whereas our copper cables can get EMI and RFI and all that. Okay, regulation. Additional regulation by country authorities. IEEE regulates Ethernet. So like I was saying, The FCC regulates us, that tells us what waves we can be on, or if you're pirating waves, I guess you're gonna get fired or fined. Okay. Wireless NICs, I'm sure you guys have seen these before. They can be USB form or built in, right? And what do they allow for? Well, the same thing as a wired NIC, except they let us attach to a wireless access point, giving us access to a wireless LAN. Alright. So, our wireless home router, we've talked about this before. It is actually several things. It is an integrated services router, so it works as an access point, right? Provides us some type of 802.11 for our wireless NIC to go onto. It has Ethernet ports to work as a switch, and it has routers, right? And we know it has routers because we are routing in between our networks. And what is it doing besides? How do we know it's routing between networks? Because we're going to this DSL modem, and it's probably doing network address translation and giving us a default route out here so we can get to the internet and all that fun stuff. But that's for a different section. Anyways, so that's what's built in. And so what is a wireless access point doing? It's providing an SSID, or a service sent identifier. And that's what we're going to connect to, like it's LCSE wireless LAN, or whatever they call it nowadays on campus, or whatever you name yours. So that's actually, yeah, that's what a SSID is. Okay, so that's the functions it's doing. So probably looking at what businesses are actually doing, because wireless access points change a little bit. Okay, so we have probably an enterprise wireless access point, and if you walk down the halls of MTV and look up, you see these Cisco devices that are wireless access points. And they could be two types. They can either be controller based or autonomous. So autonomous means we program each one individually as you would your home. We tell them what channel to be on their frequency and what their SSID is going to be, and program them much like we would a switch, and that's an autonomous. And so if we're in a real big business or have a lot of access points like LCSC, we're going to use a controller based access point, which I guess they don't have a picture here. We'll probably be going over in a second, but it actually is going to feed into the data center, and it gets its image and all of its configuration through there, and we program it through that controller. And yeah, so what it does, the controller does, is it allows different access points to see what frequency the other ones are on, how much they should charge their, like how much power they should put sending out their signal, depending on how close they are, right? Because if we are just bumping our system all the way to the top, we're going to cause interference for the other access points and actually can mess something up. Same with putting them all on a different channel. They need to be spaced out. That's what we'll be going over in a few. But anyhow, so wireless controller takes a lot of the hassle out for us. Sometimes if we're not set up just right, the only problem is how it's doing that is the two closest access points. So if it has 4 super close access points, it could actually cause interference. You might have to manually construct it. But anyways, these are going to be sending out the SSIDs. They're a real wireless access point. They probably have built-in, especially now, they have built-in radios for both 5 gigahertz and 2.4. Unless they are an AC access point, then we know that they are probably only broadcasting 5 gigahertz. Alright, so then our wireless NICs say, hey laptops, connect to the access point, and yeah, that's what you're seeing right there. Okay. Oh, it looks like I was early. So here's our autonomous. As I said, we program these similar to home use, and they're fine if we have a small office or something like that, but when we have lots of access points, then we need this wireless LAN controller, and they actually now, they can be virtualized in a data center. They can be a physical device in a data center. They actually are built into some switches now. So yeah, it's there's some different ways uh, to do this. And if I guess we look at the instruction, it just says controller-based APs are server-dependent, right? So here's the downfall: is we usually need two wireless LAN controllers, because if this wireless LAN controller controls all the access points across LCSE, and then this cable is cut or this thing crashes, guess what? We have no wireless network. So we want a backup one when we go into our wireless LAN controller. So it's another form of a redundancy that we should incorporate. Anyways, small wireless deployment. Oh, some Cisco products that are ideal for you. Okay, so intro level looks a lot like your home device. Uses a GUI. Apparently, you can power it through PoE, like a real access point, or through normal power. Then we get a little fancier mid-level businesses APs. You can actually do them GUI or CLI. Supports clustering with a single point setup. Powered using AC or PoE. Oh, I forgot one other way on the newer Cisco access points, and I think that's what this is actually saying here with this single point setup, is the newer Cisco access points actually can have a wireless controller built into them. So one AP can actually be a wireless controller for, I think, 20 others, and so that'd be another way of forming redundancy there. Very cool. Then this AP, I would still call this small. I don't know, but mid-level, small business, configure using GUI, sports controller, less clustering technology, powered by AC. And if we look over here, it says it's ideal for small to mid-sized organizations. Probably, I guess, easy to manage, but I would say mid-sized to large is going to go with this, with controller base right here. Just because if you get over, I don't know, 20 access points and you're going to pull those out with newer technology, probably every 5 years at least, then you kind of want a controller base because it's a lot less work for your staff. Alright, so large wireless deployments. Let's say our business can't afford cloud-based. Well, Cisco acquired this Cisco Meraki, which used to just be Meraki, and their cloud-managed architecture. And so what that means is your controller is actually in the cloud. Instead of have to purchasing a cloud, you purchase Meraki devices, and in the support that you pay for it every year or every 3 years, whatever your licensing is, it pays for this. The bad part is these other access points we're talking about, if you don't pay for support, you can still use them, but most people pay for support. So you're fine. So the Meraki, you pay for support, you get your cloud-based controller. This actually works with switches. They have Meraki switches, Meraki access points, maybe Meraki routers, and so you get the single pane of glass, and you get big enterprise features for not big enterprise prices, really, just a continuous subscription. So this is what the Meraki controller looks like, and this really, it's unfortunate that you can't see a big picture of it, because this is actually what a Cisco controller looks a lot like as well, except you would be going to a server rather than the cloud. And here's some Meraki access points. Okay. Large wireless deployment solutions. So here's our controller-based access points. These ones are what you're going to see inside of LCSE or hospitals, those type of businesses. This one right here is very cool. What it's going to do is the Cisco AeroNet 600 series. You just plug it in at home, and it'll form a VPN and give you wireless internet at your home, allow you to telecommute. So the person doesn't have to do anything. They just plug this thing in. As long as they have internet, it's going to go back to the home office and dial home and get them inside the network using VPN. These big beefy things, these are what we call wireless mesh, and this is where we go point to point or point to multi-point over great distances. Or maybe we're just doing outdoor Wi-Fi, and so at that point it wouldn't. When we start talking about antennas, we'll see that. So lightweight, anything that is controller based is called a lightweight access point. Why? Because if you were to steal this thing, it needs a controller to get its image, and so it is a worthless piece of junk if it doesn't have a controller, right? There's no iOS on it. It has, basically it's just Flash, and so you can't use it without a controller. And so then they talk about controllers for small to medium-sized businesses, which I kind of told you about. Here's what they look like. This controller right here could sit in the back of a router. If you look in some of our routers in the classroom, they have a wireless LAN controller, but it's old. Can't use them anymore. They've ended life there. But anyways, once again, they don't let us look in the actual controller picture. If you guys are interested, our 3560 has a wireless LAN controller in it, and I would be happy to show you what it looks like. Alright, type of antennas. So, we have several types of antennas for what we're doing. Our most common is this omnidirectional antenna. That's what's built into most access points that are serving multiple clients. So in the typical wireless LAN, what you're using at home, what you're seeing at LCSE, those are omnidirectional antennas, and they form this weird cloud that kind of goes like this around the antenna. Anyhow, that's what it does. So now there are different types for what we're doing, right? Even if we went through the ceiling, it's going to cause interference. So we build, like, this is a patch antenna right there. Too big. The drawing is too big. Alright, so this right here, patch antenna. And so what it's going to do is just do omni, but you can mount your access point where it won't be stolen, and then or you put a really long cable, so this goes over the ceiling over here. It's got 30 feet, so you have one access point that can provide access to, because they have several, usually they have 3 for each frequency on the radio to advertise. So you could put one access point there, one patch cable there, and then you run another patch cable down here, right? So that's ran to another spot providing that, and right there. Some of the ones we've been looking at back there, let's take a gander at them real quick. Oops. So if we look back here, so they're different types, like this one or the ones you're seeing in LCSE. Their antennas are built in, whereas I guess this one has proved me wrong and it only has 2 per frequency. But these are omnidirectional antennas on there. The patch are nicer because we can go further away than this, right? But anyhow, some come built in internally, so you don't have to put antennas on if you're just serving a room. But if you want to get the most bang for your buck, you're going to probably do some patch antennas in different directions, and sometimes you're going to do a patch that only shoots a certain way. That's probably what this guy's doing right here. It's either a multi-direction or a one-to-one, but basically it's going to shoot a wireless signal of like a straight beam, and then a little bit of, it has a little bit of stuff up in here. So anyways, that's how that one works. Is it's more directional antenna. So I'll give you a Cisco's rundown. Alright, omnidirectional. Factory Wi-Fi gear often uses basic dipole antennas, also referred to as rubber duck design, similar to those used on walkie-talkie radios. Omnidirectional antennas provide a 360 coverage and are ideal for open office areas, hallways, conference rooms, and outside areas. Directional antennas. Directional antennas focus the radio signal in a given direction. This enhances the signal to and from the AP in the direction of the antenna, pointing, providing stronger signal strength in one direction and less signal strength in all other directions. Yagi, type of directional radio antenna that can be used for long distance Wi-Fi networking. These antennas are typically used to extend the range of outdoor hotspots in a specific direction or reach another building. Okay, so this is a Yagi antenna right here. I would consider these are directional antennas, but they basically have a Yagi besides. Well, no, they're probably shooting off that dish, so I'm gonna take that back. But these cans, the Pringle can, anything that looks like a Pringle can is a Yagi. The rubber ducks are, well, they don't have any rubber ducks here, so this would be a rubber duck. And these ones are flat and round. If they were pointed like the ones you typically see, like if we go back, like those ones show that they are 5 gigahertz. They're kind of flat and round, whereas these ones are pointier. Those are 2.4 gigahertz rubber duck, omnidirectional antennas. Alright. So, two types of wireless modes. Ad hoc. Ad hoc is a peer-to-peer network. We can do it on any laptop. Say a laptop will become a wireless access point, and then it could share information with other people. Our others is infrastructure mode, where we're actually going to an access point serving as the SSID that will then service it across a real network, right? So ad hoc is for, I don't know, we could share a printer or share devices if we're in a pinch, whereas infrastructure is going to be a long-term, much higher speed connection, right? So more about ad hoc. Independent BSS, which they haven't went over that yet, but that means a basic service set. Number of access points, none, because it's just your wireless NIC in your computer saying you can do it, that you're doing that. A very small coverage area. Infrastructure mode, infinite amount of access points. I guess in just a basic service set there's one. When we go to an extended service set, there's going to be more, right? So these are two types of basic service areas. We can have 2 computers, 1 computer, 5 computers. One thing is we probably only want 25 devices on a radio at one time. The more devices, the weaker our signal goes, because it takes more power to broadcast to all those guys. So this was a basic service set. Now we have the extended service set right here. So we look at it, and what that's doing is they're going to be the same SSID. This is why you can walk around LCSC, because it has an extended service set. It feeds in this area, and anywhere you go, you're still in that extended service set. You need 2 or more APs. Okay. Feel free to read a little more about those if you are interested. 802.11 frame. Okay, this is kind of a nightmare. Just to let you know, we could spend an entire year probably studying the 802.11 frame. Alright, so we're going to keep it simple. Frame control identifies the type of wireless frame that and contains the subfields for the protocol version, frame type, address type, power management, and security settings. This is going to make more sense on identifying the type of wireless frames. We're going to find out there's multiple types of frames, and so that's going to be coming up in after this. Duration, typically used to indicate the remaining duration needed to receive the next frame transmission. Address 1 usually contains the MAC address of the receiving wireless device or AP. Usually contains the MAC address of the transmitting wireless device or AP. Address 3 sometimes contains the MAC address of the destination, such as the router interface, aka the default gateway, you guys already knew that, to which the AP is attached. Sequence control contains the sequence number and fragment number subfields. The sequence number indicates the sequence number of each frame. Fragment number indicates the number of each frame sent of a fragmented frame. Usually missing. Address 4, usually missing because it's only used in ad hoc mode. And who does that? Payload contains the data just as always, and then of course we have an FCS to make sure we received the frames correctly. Okay. Frame control field. So, inside our frame control we have the protocol version. Provides the current version of 802.11 protocol being used. Receiving devices use this value to determine if the version of the protocol of the receiving frame is supported. Frame type and frame subtype determines the function of a frame. A wireless frame can either be a control frame, a data frame, or a management frame. Those are 3 types. Keep those in mind. These are multiple subtype fields for each frame type. Each subtype determines the specific function to perform its associated frame type. TODS and FromDS indicates whether the frame is going to or exiting the DS and is only used in the data frame of a wireless client associated with an access point. Alright, so now you're asking, from DS, to DS, what the heck's the DS? Alright, that just means distribution system. Okay, so that's what's going on there. Alright. Let's see what else we have. More fragments indicates whether more fragments of the frame, either data or management type, are to follow. If it's a retry, power management indicates whether the sending device is active mode or power save mode. We're going to learn about that more in the future. More data indicates to a device in power save mode that the AP has more frames to send. It is also used for APs to indicate that additional broadcast multicast frames to follow. Security indicates whether encryption and authentication are used in the frame. It can be set for all data frames and management frames, which have subtype set to authentication. Reserve can indicate that all received data frames must be processed in order. Okay, what do we have here? It's just showing you, I guess if you guys want to look at these, capture some stuff from Wireshark. I actually think you need a special version of Wireshark though to capture wireless traffic. So anyways, if you wanted to see this, you could, just as we can see stuff from Wireshark about Ethernet. Alright, so here are types of frames which go in our frame type. So, management frame, used in the maintenance of communication such as finding, authenticating, and associating with an access point. So, finding that wireless signal, putting our password in so we can do other things. Controlled frame, used to facilitate in the exchange of data between wireless clients. So then we have a control frame. It says, hey, are you who I'm looking for? So we kind of establish that there. Then we have our data frame, used to carry the payload information, such as web pages and files. So these two come first, then we send the data. Probably control ends it. If we wanted to sign into a different SSID, do a different management. And that's as general as I can get. Just showing our same frame from before. Alright, so management frames. What are different types? And here's our subtype. Association request frame sent from the wireless client. It enables the AP to allocate resources and synchronize. The frame carries information about the wireless connection, including supported data rates and the SSID of the network to the wireless client that wants to associate it. If the request is accepted, the AP reserves memory and establishes an association ID for the device. Association response frame, sent from the AP to a wireless client, containing the acceptance or rejection to an association request. If it is an acceptance, the frame contains information such as an association ID and supported data rates. Reassociation request frame. A device sends a reassociation request frame if it drops from the range of the currently associated AP and finds another AP with a stronger signal. Where would this happen? In an extended service set, right? This is how you walk from one room to another. The new AP coordinates the forwarding of any information that may still be contained in the buffer of the previous AP. Reassociation response frame. Sent from an AP containing the acceptance or rejection to a device. The reassociation request frame. The frame includes information required for the association, such as association ID and supported data rates. Alright, so same as the association, same as the association response frame, except with a re in front of it. Probe response. Sent from an AP containing capability information such as supported data rates after receiving a probe request frame. Beacon. Sent periodically from an AP to announce its presence and provided the SSID and other pre-configured parameters. So beacons are coming from APs all the time. Disassociation frame. Sent from a device wanting to terminate a connection. Authentication frame. The sending device sends an authentication frame to the AP containing its identity. Deauthentication frame. Sent from a wireless client wanting to terminate the connection from another wireless client. Alright, so those are fun. The two, you want to look at probe. Right, so if we look here, sent from a wireless client when it requires information from another wireless client. Right, so we have probe request coming from the client, beacon sending, hey, so it's probing for information, probably about the beacon, right? So the probe request, the beacon sending out there, hey, I'm an access point, this is my SSID. Then this access point probes it, says, hey, what kind of authentication, or something like that, right? Control frames. Alright. So this has to do with collision avoidance. Right? So remember, collision avoidance says, alright, it's your turn to send, it's your turn to send, it's your turn to send. It's not like collision detection where if it's supposed to avoid all collisions, right? It's because it gives you an allotted time to send. So how is it doing that? The request to send frame, right? The RTS and the CTS frame provide an optional collision reduction scheme for APs with hidden wireless clients. A wireless client sends an RTS frame as the first step in the two-way handshake, which is required before sending data frames. Alright, so maybe I'm wrong there. Because that says it's additional. So CA, I guess CA, you are just, either way, it's waiting to say, hey, is the line not busy, and can I send? Alright, and that's the grasp of CA, whereas remember CD is after collision happens, how we're going to fix this, right? So clear to send frame. A wireless AP responds to an RTS frame with a CTS frame. It provides clearance for requesting wireless client to send data frame. CTS contributes to collision control management by including a time value. This time delay minimizes the chance that other wireless clients will transmit while the requesting client transmits. And we have acknowledge. After the receiving a data frame, the receiving wireless client sends an ACK frame to the sending client if no errors are found, and if the sending client does not receive an ACK frame within a predetermined period of time, the sending client resends the frame. Alright, so here's our collision avoidance in a nutshell, right? So how does it work? Here we go. Well, now it does look like we're still using those control frames for it, but it's not what they said on that last one. Anyways, Some interesting things. Wireless is always half duplex. It's half duplex, shared media. That's why we need CSM-CA, right? We need CD where when we have hubs and a half duplex environment. That's when collisions are going to occur. All right, so request to send, clear to send, data sent, acknowledged. How does this work? Here we go right here. So they start sending. The wireless access point assembles the frame. Alright. Then it asks, is it clear to send? If the answer is no, wait for a random back off time. If the answer is yes, transmit the request to send. Does it receive a clear to send from the access point? If no, wait for a random back off timer. If yes, transmit application data end. But this is why wireless, even though it says we're getting 600 meg, you're getting half of that, because just like when a wire all sends one way, basically when we're sending and receiving, it's just coming. Why is it half duplex? It's sending it at one time and then wait, see what's going to happen, doot doot doot, and then it sends back. You know, it's got to wait for this stuff, and it's not sending and receiving at the full time. But AD is supposed to be able, AC and AD are both supposed to do full duplex. I think AC was in the second wave. I don't know if we're there yet. I should look that up. And AD, I'm sure, should be able to as well. So we don't have, so I guess it wouldn't be using CA all the time. Alright. So, here's an important thing. The authentication, right? So this access point sending up beacons, so we send a probe request. Hey, oh, so we have to authenticate, or maybe we don't, maybe it's open, then we wouldn't have to authenticate. But in this case we have to authenticate, so then it authenticates to the access point, then it associates, and we've all seen this probably spinning down in the bottom because it never happens fast enough for us, or something weird has happened. So down in our bottom right we could see that. So what are we associating with? Well, if you don't have a home router, you would see this. And by the way, if you're using a home router and using mixed, you're wasting half your network, in my opinion. You have two radios, and your 2.4 is almost always going to give you a better signal, so you're never really on the 5 gigahertz. You're never going to get that speed, so don't use this mixed. Actually set up an SSID that is dedicated to the 2.4 into the 5 gigahertz, so if you're close, you can connect and get the 5 gigahertz speed. If you're distant, you can get the 2.4 gigahertz, but this mix mode, you are almost always, if you look, you're going to be on your 2.4. Okay? That's just my personal advice. Alright, so then we have our network mode. When we set these up, this is setting it up, our most basic service set, right? So we have our network mode. So it's saying mixed here. So the mixed, it would be, another one would be, we just pick 2.4 gigahertz, the 5 gigahertz. I guess if we're running AD, maybe we could pick the 60 gigahertz. So anyways, they're doing mixed. Boo. SSID. So this is what's going to be advertised, right? Home net. So we could go to here and let's see what we have here, right? So apparently my access point can't even see. No, I must not. This access point must only support 2.4 gigahertz because I have Brute 2.4 and I have something that says a 5. That's how I know I'm on the 5 gigahertz, or I'm on the 2.4 gigahertz, as I've been preaching about. Okay, so radio band. This is the channel, now the radio band, I guess, would be. Okay, I take it back. Network mode. This wouldn't be 5 gigahertz. This is AC, AD, BG, whatever your thing supports. So mixed, still multiple standards. I'd still crank it up. Hey, if you got N devices or AC devices and you're paying for them, you might as well go full. But I guess if you have a bunch of old stuff, go mix mode. I apologize for that, but alright, SSID, still your unique identifier for your access point. Radio band, That's going to be our 2.4 or 5 gigahertz. This auto is going to be the thing I hate. The channel width, that would be on your, I believe that should be on your 5 gigahertz setting. So, because you could do, I don't think on the 2.4 you can make, you have a 20 megahertz channel or 40 megahertz channel, and maybe some more. Give me a second. Alright, yeah, that's right. 2.4 allows 20 and 40. I think that's what I said. That'd be just 220 megahertz. But a 5 gigahertz, this is where we get more speed, is our channel width can actually be 20, 40, and 80. So the difference is going to be, the bigger our channel, the more speed we can set off of there. So if we want max speed settings, we're going to need 80 megahertz, that kind of thing. But as always, the bigger we make that, the worse our service is going to get. So we're limited to speed, but yeah. So then we go to channel settings. So this refers to the frequency that's being transmitted to wireless data. Wireless routers and ABs can choose a channel setting manually, or if there's interference with another AP. In figure 1, the channel is manually set to 6, which is 2.437. I'm not going to ask you, I don't think you should, on this basic CCNA, it's not going to ask you this, but you are going to know how far to space channels, and we're going to go over that on the 2.4 here in a second. What do we have here? Oh, then we have our authentication, right? Our security modes. We have WEP, which is worthless. We have WPA or WPA2. As it says right here, always enable the highest level. For home or small office, you'd use WPA Personal. For business, you'd probably use WPA Enterprise. Alright, so then there's encryption. So we pick our security mode. Then we're going to pick how we're encrypting our traffic. And so on WPA 2 we can use AES, or we could go to WPA and use this TKIP, or there's CCM as well. We'll talk about the encryptions. I believe that's in the next couple figures. Then we have the password to get in there. Alright, and the WPA2 is dynamic, where WEP, we could crack that password in like 2 minutes. WPA2, you're going to just do a brute force attack on it. But, yeah, anyways, I'm sure you guys understand the passphrase to get logged in. Alright, so passive and active, as with all, it's never going to make sense. So, passive. Now, for me, I would think this was active. Passive. The access point openly advertises its service by periodically sending broadcast beacon frames containing the SSID supported standards and security settings. The primary purpose of the beacon is to allow wireless clients to learn which networks and APs are available in the given area, thereby allowing them to choose which network and AP to use. Okay, so passive means it's actively doing this stuff, right? So active mode is the opposite. So remember, passive means, active means you actually have to try. So wireless clients must know the name of the SSID. The wireless client initiates the process by broadcasting a probe request frame on multiple channels. The probe request includes the SSID, the name, and standards supported. Active mode may be required if an AP or wireless access point router is configured to not broadcast beacon frames. Okay, so this would be hiding your SSID, which is, I don't believe they've fixed this, but there's actually a way to, if you're hiding your SSID, that because you're hiding that, someone can inject that wireless frame to bypass all security. So it's probably best to go in passive mode and just do really strong passwords, because even if you do a strong password in active mode, in the past there's been ways to get past because it's actually hiding that security. So even though in this part of Cisco it might say, hey, this is a good idea, it's not. So beacons are getting supported. What are the AP sends beacons, the sender sends probe requests, right? And I guess that has to do with active and passive mode. Alright, so open authentication. It's where we don't have to put a password, and you don't want to do credit card transactions on here probably, because it's most likely that unless you're encrypting in a different way, people can pick up all your wireless traffic. And then if we have a shared key authentication, this is actually encrypting your traffic, but once again, if somebody gets on there, they can probably unencrypt your traffic based on their own. What is this even saying? AP assigns an association aid to the client. Okay, so after it's associated, after we authenticate, we associate and get all that stuff. So what's it actually saying? The wireless client sends an authentication frame to the AP. The AP responds with a challenge text to the client. The client encrypts the message using its shared key and returns the encrypted text back to the AP. So hopefully you guys will learn about public and private keys, and this will make more sense when you're in Security Plus. The AP then decrypts the encrypted text using its shared key. If the decrypted text matches the challenge text, the AP authenticates with the client. If the messages do not match, the wireless client is not authenticated because it didn't use the right shared key. Okay, and access is denied. After a wired client has been authenticated, the AP proceeds to the association page. As a part of the association page, we go into this. The wired client forwards an association request frame that includes its MAC address. The AP responds with an association response that includes the AP's basic service set ID, which is the AP of the MAC address. The AP maps the logical port, known as the association identifier, to the wireless client. The aid is equivalent to a port on a switch that allows the infrastructure switch to keep track of the frames destined for the wireless client to be forwarded. Frequency channel saturation. Okay, so what they're talking about on here is DSSS and HSSS and OFDM. This is how these different frequencies are sending their traffic. Okay, so we'll read about them. Direct Sequence Spread Spectrum, DSSS. DSSS is a spread spectrum modulation technique. Spread spectrum is designed to spread a signal over a larger frequency band, making it more resistant to interference. With DSS, the signal is multiplied by a crafted noise known as a spreading code. Because the receiver knows the spreading code, and when it was added, it can mathematically remove it and reconstruct the original signal. In effect, this creates redundancy in the transmitted signal in an effort to counter the quality loss in wireless medium. DSS is used by 802.11b, also used by cordless phones in the 900 MHz, 2.4 GHz, and 5.8 GHz bands, CDMA cellular, and GPS networks. The CDMA cellular, in my experience, it's a emergency connection that you would have on its emergency wireless connection. Alright. FHSS, frequency hopping spread spectrum. FHSS also relies on spread spectrum methods to communicate. It is similar to DSS, but transmits radio signals by rapidly switching a carrier signal among many frequency channels. With FHSS, sender and receiver must be synchronized to know which channel to jump. This channel hopping process allows for more efficient usage of the channels, decreasing channel congestion. Walkie-talkies and 900 MHz cordless phones also use FHSS, and Bluetooth uses a variation of FHSS. FHSS is also used by the original 802.11 standard. Okay. Orthogonal frequency division multiplexing. OFDM is a subset of frequency division multiplexing in which a single channel utilizes multiple subchannels on adjacent frequencies. Subchannels in an OFDM system are precisely orthogonal to one another, which allow the subchannels to overlap without interfering, but we all knew that. As a result, OFDM systems are able to maximize spectral efficiency without causing adjacent channel interference. In effect, this makes it easier for a receiving station to hear the signal. Because OFDM uses subchannels, channel usage is very efficient. OFDM is used by a number of communication systems, including 802.11a, G, N, and AC. Alright. Selecting channels. Alright. So, on these radio waves, we're either using UHF, SHF, or on the newest one, EHF, right? And that's only AD. That's at 60 gigahertz. But depending on whether we're using 2.4 or 5 gigahertz puts us in, just like we have colors of lights, we have frequencies of microwave, I guess. So anyways, so what this means is, right, is we have a wave. And so on B, even though we're on channel 1, it's going to bleed into clear to where channel 6 is going to be good, right? And so from channel 6, we go to channel 11. So basically we check 1, 6, or 11. We have to go 5 up because we have, as it shows here, we have frequencies bleeding in from the other channels. Now why is 11 fine? We're basically done after that, so it's not bleeding that way. But just the wave is going to bleed into there. So if we didn't, like say if we put on channel 3 and use channel 1, we're going to cause a bunch of interference for both these channels and screw up everything. Alright. Here's it. It's actually showing it. So channel 1 is 2.412, channel 6 is 2.437, and channel 11 is 2.462. Now, notice this says with a width of 22 megahertz, right? So depending on our channel width is going to depend on where we hit in here. Alright, and this is DSSS with B. Alright, so still on 2.4, right? This is our G, this is our OFDM, but this is on the 2.4 gigahertz, and similar effects, right? As you can see, channel 1, 6, I guess we can use channel 13 again on this one. Did not know that. But anyways, if you're using G or N, right, because this is N on the 2.4, you could hit here. Alright, so now we're using N with 40 megahertz, and as you can see we're still on the 2.4, so this is 2.4 with a bigger width. So the other ones I don't believe we can adjust B's width. It's when we got G. Must still be 20 megahertz. Let's see if it says it right there, because I can't remember off the top of my head. But N, we can go into the 40 megahertz, as you see. So this is where we could get the most data off of our 2.4. But you also can see channel 3 ruins everything down to there. And channel 11, we only have basically 2 channels in a period of time, because we're increasing that channel width. Why do they not show 5 gigahertz? Because there's a lot more channels to use. So you could probably find a open one, unless you're a wireless internet service provider. When we plan a wireless network, well, we want to make sure our channels aren't interrupting each other. Is basically what they're showing. Someday I will probably show you how I choose mine, because it takes more than most. Probably where we do bad development as a network designer is we do look at this, but is this a 2-floor? Because if we then put the same, like say we put channel 1 here and channel 6 here, channel 11 here, or say it was so then what do we put here? What? Because we're hitting everything, right? So we're gonna have to have some interference probably at some point. But where this also gets more complicated was, what if this is a 2-story building? Well, then we want to, for our least amount of interference, we actually want to make this one 1 on the 2nd floor and this one 11, because it's going to bleed down. It's going to go through those walls, and if they're on 1, we have a ton of interference from ourselves, and that's the last thing we want to do. Okay, so anyways, you want a 3D view when you're designing these networks. And that's also why we want to check our power, and that's where a wireless controller can help us out a lot, is it could adjust those channels for us. Alright, so wireless threats. Rogue APs, right, which are unauthorized access points, intentional or willingly used for, so they can be either malicious or not. You putting up a hotspot in a wireless network off your laptop would be a rogue access point. Now, you could have an evil twin if you're actually maliciously saying, hey, I'm LCSC wireless LAN. That's called an evil twin, and it's more than a wireless access point. Wireless intruders, people that aren't supposed to be in your network getting in. They can intercept data, or they can DOS. Now, a rogue access point could DOS because it could say, hey, I'm LC wireless LAN, have no internet, or just pose a man in the middle of the threat. Or you can just cause so much interference that it's going to crash, or use up all the access points, similar to wired networks on that. So here's our DOS attack. How can we get DOS? Well, if we use default passwords and usernames, it's probably pretty easy to get in our network and shut it down. Another thing that probably DOSs us, and we don't even mean to, is we've said that, hey, these phones, these microwaves, also sometimes run on 2.4. My dad, his wireless internet used to go down every time his cordless phone would ring. It would kick him off the internet. So, probably bad if you're making phone calls and doing business on the internet at the same time, because you can only do one or the other. I don't know, you could shut down a malicious user could get in if you had default passwords, take off your default gateway, or run it through. This would be accidental interference. There's also managed interference, where you'd be getting similar interference, destroying frames because you have another wireless access point too close on the same band. Anyhow, 2.4 goes further, but it's more prone to that interference because there's less channels. Management frame DOS attacks, spoof disconnect attack, so it says you actually don't want to connect. Clear to send flood, so there'd actually be collisions occurring. These disconnect attacks, actually an access point, Cisco makes technology where it can surf for rogues and actually say, hey, actually this is a bad access point, don't talk to them. So it could probably detect this happening and do something like that, but also if it's just a rogue access point, it'll say, hey, that's not actually LCSC wireless LAN. Don't connect, but it does waste some of the access point's power. Rogue access points. This is called Cisco Prime, this window you're doing. It works with wireless LAN controllers. You can build cool maps like this, and so right here shows you where your power is too strong for someone to be around. This is your really good wireless network. This is pretty good in the green, and this is kind of getting scary, but it's showing you your wireless signal as planned. You draw this all out, you put how thick these walls are, what kind of interference you have, and then you go from there. Yeah, so I can show you, I can kind of show you a version of this, but it's a fairly expensive software. It gives you a single pane of glass. You can manage switches, wireless access points, routers through this, similar to the Meraki. But anyway, so the good thing about it is your access points can scan using Cisco Clean Air and pick up these rogue access points, and if you have it set up with GPS, your Prime can show you right where that access point is, or at least close to where it is. Man in the middle, it's where you intercept the data before sending it on, so you can, you know, the encryption key to decode, and it's a heart attack to stop. That's why we have to use a lot more than just WPA2 if we're doing like in banks that are using wireless networks and stuff like that. But this is the evil twin, man in the middle, that I was talking about earlier. Take a look at it. Alright, so SSID cloaking, that's what I talked about. APs, some wireless access point allow SSID beacon frames to be disabled. Wireless clients must manually identify the SSID to connect there, but it's actually not a great idea. MAC address filtering. This is one way to secure something, except MAC addresses can also be spoofed, but it'll make you a lot more secure where you have to be that MAC address to get on. Open system authentication means it's just open and scary. Shared key, we're actually going to have an encryption of our data floating around in the air. And once again, we want WAP2 if we can, or at least WPA, WEP. You might as well not have anything on there, but most people don't anymore. So here's our shared key authentication. WEP, as I said, was original, obsolete, sucks because one of the keys is not dynamic. It stays the same, and it makes it very easy to crack the encryption of your shared key password just through the traffic being sent. WPA, Wi-Fi protected access. It's great. Like I said, we can use TKIP on it, which is Temporal Key Integrity Protocol. Pretty strong algorithm, but even better one is this AES, which is Advanced Encryption Standard. We can use it for other things besides this, but it's stronger. I thought one of these should say CCM, but they're not going to talk about CCM, so we won't either. We'll just keep going. Nope, they just talk about TKIP and AES, so nope, there's CCMP. It's in AES, I guess. So let's read them both. TKIP is the encryption mechanism used by WPA. Provides support for legacy wireless LAN equipment by addressing original flaws associated with the 802.11 WEP. It makes the use of WEP but encrypts the layer 2 payload using TKIP and carries out the message integrity check the mic in the encrypted packet to ensure the message has not been tampered with. AES is encryption method used by WPA2. It is preferred method because it aligns with industry standards IEEE 802.11i. AES performs the same functions as TKIP, but is far stronger method of encryption. It uses the counter cipher mode with block changing message authentication code protocol (CCMP) that allows destination hosts to recognize if the encrypted and non-encrypted bits have been tampered with. Authenticating a home user. So we have personal authentication and enterprise. And so personal authentication is where we're using these pre-shared keys, right? So where we actually make up the password. In enterprise, we can use a thing like Radius, and Radius will actually let us use like our Active Directory sign-ins. It's known as 802.11x. It uses EAP and all this. We can also use TACAX Plus to authenticate, which is a Cisco proprietary, which does a similar service as Radius, but actually separates the authentication servers. They can be different, so if one server gets compromised, you still have a AAA server. Those are servers. Alright, so authentication, authentication, and wait, no. Okay, so we have accounting over here. We have authentication and authorization. Sorry, those ones get in my head. Authorization and authentication. That'd be AAA. And the Radius does it all on one server, whereas TACAX will do it on another. I'm not talking about it here. But anyways, that's where we'd see those 802.11 enterprise. They use some kind of server like that. As you can see, they're using enterprise, but actually they're using a shared key here. So, but do they not have it where you use Radius? Oh, my bad. Yeah, Radius actually still uses authentication. So it's going to authenticate to the Radius server, and then you still have to use a sign-on, such as how you'd log on to the domain. Do have that set up in the classroom if you want to look at that. Alright, planning a wireless network. Well, you need IP addresses, internet connection. It can be a DHCP controller, SSID, a wireless LAN. If you guys haven't set this up, you can do this in Packet Tracer. Packet Tracer has this exact wireless N router that is so legacy and nobody would ever use again, but Cisco owned Linksys. I believe they sold them now, but you can set up all of this stuff if you never have. It's a very good idea because it's a simple task. So go into Packet Tracer, and there is a wireless router to use. And when you go there, it's going to have that same GUI interface as that. Anyways, I'm not going to go over the basics. If you can't figure out these orange ones that just say switch, are your switch, or I guess they just say are Ethernet ports. The one that says internet is your router port because it's connecting networks. Here's your antennas, wireless access point integrated inside. That's how you're going to set that up. If you never have, again, I have some of these Linksys as well, and we could do a lab where we would do it, but it is extremely boring. This is just setting up a DHCP scope. Hopefully you've learned that in server already. If not, go over that again because it's basically the same thing in this little thing. I'd run a real server if you have the chance. Configure your management access. This is your default passwords that you need to change, otherwise anyone on the internet is going to come in there, try a few default passwords, and they could man in the middle of you, change your firmware up, cause all kinds of problems. They probably won't though. Alright. Connecting wireless clients. I think everyone has probably gotten on the wireless internet at LCSC. If not, once again, ask one of your friends. I'm sure they can show you how. Well, so if we're having problems. Here we go back to our old TCP. So this is the advanced TCP/IP, or the updated TCP/IP model, right? So we could do bottom up, top down, or divide and conquer. Top down, start at the application, go down, see where a problem is. Bottom up, start at the physical layer, go up. Divide and conquer, start in the middle, go somewhere with it, try to figure out what's wrong, right? So how does that work if we're not connecting? Alright, so if I was starting at the bottom down, I would say, hey, can I see wireless? Do I have a wireless card in here? Is my computer on? That's probably some good questions. Then I'd go to the data link. Do I have the drivers, right? Because remember, part of that data link is going to hand off to there. Do I have the drivers for this? Okay, so then am I getting a network connection? No. And so am I getting some kind of IP address, right? When I go to Wireshark, can I see anything being transported out of my wireless NIC? Is it getting anything back? Application. Can I actually see my wireless network? What's going on here? Like, where is it failing, right? Because we know if we can't even get on here with our MAC address, like if we can't get authenticated, if it's failing halfway through, it's probably a bad password or something, or our drivers aren't supporting this network, or they don't support this encryption. An example of that is older iPhones could not handle AES, and so there's no way for you to log on. They would fail every time, and so you had to drop it down to TKIP on your authentication to do that. But if your MAC addresses can't get to the access point, data link. But you can start from the bottom or the top, right? Web traffic, whatever. It's up to you, but that was just my example. I think this is theirs. Go ahead and take a look at it. If your network is slow, upgrade your wireless clients. Split the traffic onto different frequencies. As I told you, right, Home Net 5, Home 2.4, I would always do that because you could load balance the radios at least, right? And like I said, we don't want to have more than 25 devices on here, especially a home device. We probably don't want to have more than, 10 devices on a home device, unless it's a higher end one for sure. But anyways, upgrade the clients. I would also say, hey, maybe you want to upgrade this, maybe you want to add more access points or put a switch in, but they don't say that there. So if you have slow traffic, split the traffic and do that. Updating firmware, this is called, flash it. Caution, on these ends you could put in a lot of open source stuff that would give you a lot more tools. I'm not going to tell you how to do that because you can break it completely. Go ahead and Google it, break it on your own. It's a great idea though. You don't really know something until you've broken it. Alright, so Ann gave us some other stuff, and I'm surprised we haven't seen that. I'm sure we have, but I don't know what this FIPS is, but MIMO is multiple input output. That's what happened in N. It means you could send out of one radio and receive out of another. That's how you're getting that high speed. Cisco Clean Air technology, it's checking their waves, looking for interference, looking for rogue access points, that kind of thing. Cisco Flex Connect, I believe that is a BYOD thing, but I do not remember. Band select, I would guess that's just telling you what frequency to put it on. Anyways, take a look at those if you're interested, or send me an email and I can give you more information on that. That was wireless, and it was an extremely long chapter. I hope you're still awake. Make sure you